Ladies and gentlemen, welcome to this lecture on the integration of electric vehicles into the electrical grid. I'm Gautam Ram and I'm an assistant professor at the Delft University of Technology. In this lecture, we'll first see what are the current trends in the adoption of electric vehicles in the world. Next, we will see what are the different types and power rating of electric vehicle chargers around the world. Finally, we will see what is the impact of mass deployment of electric vehicles and their integration into the electricity grid. Let us first start by looking at the figures of electric vehicle adoption in the world. Based on the International Energy Agency, there were 11 million electric vehicles in the world in 2020, having seen a steady rise over the last decade. China has the most significant stock of electric vehicles, followed by Europe and the USA. If you take the case of the Netherlands, where Delft University is located, there were more than 300,000 vehicles in the Netherlands in 2020, which were either a battery electric, a plug-in hybrid electric, or a fuel cell electric vehicle. This is 3 times the figures from 2016, so that's a dramatic increase. In 2020, 1 in every 5 vehicles that was sold in the Netherlands was an electric vehicle, and by 2030, all new cars in the Netherlands must be emission-free. The more the vehicles, the more is the demand for charging stations for charging the vehicle. And so the number of public charging stations has rapidly grown as well. The growth rate in public charging stations in the Netherlands has been almost the same as the vehicles, maintaining a 4:1 ratio of vehicles to charging stations. To understand the impact of electric vehicle charging on the electricity grid, it is vital to first understand the vehicle's energy and power demands. The battery capacity of EV batteries ranges from those in two-wheelers, which typically have 1 to 5 kilowatt hours of battery capacity to provide 50 to 125 kilometers of range, and goes all the way up to electric buses and electric trucks batteries that have a battery of typically 50 to 500 kilowatt hours, providing a range of 50 to 500 kilometers. In between these two extremes, we have electric car batteries, which on the other hand have a typical battery capacity between 30 to 100 kilowatt hours, giving a range of 200 to 500 kilometers. This means that it can take several hours to charge electric vehicle batteries because of their large capacity. Do keep in mind that these figures for vehicle battery capacities and range are generic and will vary from vehicle to vehicle based on its application. Let us now look at the EV charging power levels. In case of alternating current or AC charging of electric vehicles, AC power from the electricity grid is fed to the onboard charger, which is an AC to DC power converter that converts the AC power to direct current or DC power suitable for charging the battery. Due to the size and weight restrictions inside the vehicle, the onboard charger is typically limited in the size and weight as well, and the maximum power is usually less than 22 kilowatts. Therefore, the solution to increasing the charging power beyond 22 kilowatts is to move the AC-DC converter outside the vehicle and place it in an off-board charger. This is referred to as direct current or DC charging and can have a maximum power between 50 to 350 kilowatts. For alternating current or AC charging, the Type 1 connector commonly used in USA and Japan has a maximum power of 19.2 kilowatts. In contrast, the Type 2 connector, which is widely used in Europe, supports 3-phase charging and has a maximum power of about 22 kilowatts. And Tesla uses its proprietary connector in the USA with a maximum power of about 11 kilowatt. On the other hand, there are 3 different plugs for DC or direct current charging of electric vehicles, namely Combo, Shademo, and Tesla, and they support charging powers up to 400 kilowatts and battery voltages up to 1000 volts. The newly proposed Chao-G plugs increase this even further, facilitating charging up to 900 kilowatts and supporting battery voltages up to 1500 volts. Okay, so why are electric vehicles and their chargers relevant to grids and grid operators? Let us start by comparing simple household appliances and the power that they consume. At the left, we have electronic gadgets like mobile phones and TVs that consume power in the order of tens or hundreds of watts. Next, we have domestic appliances like washing machines, ovens that consume 1 to 3 kilowatts of power. But this is nowhere close to the power levels for EV charging, which are much higher. Even slow AC chargers can be up to 22 kilowatts, while DC fast chargers can be 50 to 350 kilowatts. This means that future electricity grids will experience a significant increase in power demand due to electric vehicle charging, and this will be in addition to increased demand coming from electrification of heating and cooling. Also, the charging process of one car will last several hours with a high probability of overlap with another cars in the neighborhoods, further increasing the demand on the electricity grid. So what is the effect of this increased grid demand? First, the higher electric vehicle charging demand will increase the loading of the cables, lines and transformers in the transmission and distribution network, possibly overloading these assets if the peak demand of the electric vehicles coincides with the peak demand on this grid which is already present. In case of networks with long feeder cables, then the demand of electric vehicles coupled with distribution generation can cause overvoltage or undervoltage to specific customers located to the end of the feeders. Furthermore, in the case of three-phase networks, imbalanced EV charging because of loads on one or two phases will cause phase imbalances that might be a challenge to rectify from the grid operator side. Finally, since electric vehicle chargers are power electronic devices operating at high powers and high switching frequencies, they can inject harmonics, interharmonics and supraharmonics into the grid depending on the frequency of the harmonic with respect to the fundamental 50 Hz frequency. This can cause unnecessary resonance resulting in distortion of the voltage, flickering issues and heating of appliances. So let us now summarize this lecture. First, we saw the current trends in electric vehicle adoption with over 11 million vehicles around the world in 2020. Next, we saw the power rating and types of onboard AC chargers rated up to 22 kilowatts and DC chargers rated up to 350 kilowatts. Finally, we talked about how electric vehicles impact the electricity grid and why they're relevant for grid operators by looking at the challenges of integrating electric vehicles into the grid. We specifically looked at overloading of transformers and lines, over and under voltage, phase imbalance, and harmonic injection. Thank you for listening.